Greetings everyone, my name is Ricardo and I want to show you the project me and my colleague Luis are working on, a personal trainer powered by TinyML. Our objective is to find a way to integrate TinyML into the gym environment by creating a product that is small, battery powered, wirelessly connected, and able to identify when an exercise is being done correctly or not. Our board of choice for this project was the Seed Studio Shell NRF52840 Sense, since it fits in all the requirements for its compact size, lower power consumption, ability to recharge the battery, built-in accelerometer and gyroscope, sensors that are essential for this project, a Bluetooth 5.0 antenna, and a microcontroller that can handle TinyML models. However, we needed a way to place the board on the side of a dumbbell. We came up with a 3D printed casing that helped us with the placement while providing a secure, protective housing for the board and the battery. This way, it is possible to bring the microcontroller inside a gym, while having it protected for accidental drops on the ground and being able to operate without cables. Our main focus on this project will be to classify 3 different exercises: the biceps curl, the bench press, and the lateral raise, all of them done using dumbbells. This choice was based on these exercises working different types of muscles: the biceps, the chest area, and the shoulders. As you can see here, these are the correct ways to execute those exercises, all done by the gym instructor Clayton Nogueira. In all these exercises, a correct execution is defined by the main muscle doing most of the work, while minimizing the work done by the other unwanted muscles. For example, in the lateral raise, you want to mainly work with your shoulder while minimizing the work done with your trapezius muscle or with the lower back. With this setup in mind, we can collect data in a real environment to form a dataset. It all starts by sending a command from a smartphone to the microcontroller. The microcontroller then starts sending the collected data from the accelerometer and the gyroscope through the Bluetooth to the smartphone until the exercise is completed. The smartphone at the same time is receiving and storing all this data in either a CSV file or an online Google Sheet if internet connection is available. But how exactly is the smartphone sending commands? By using the MIT App Inventor, an Android app was developed to work as a bridge between the smartphone and the microcontroller. As you can see in this video, it searches for all available Bluetooth connections, and when the connection is established, a blue LED is activated on the board. The app will then show the sensor data of all the 3 axes of the accelerometer and the 3 axes of the gyroscope. As the send data button is pressed, all the data is stored in a file inside the smartphone. This image represents a file generated by the app. It has a name that was chosen inside the app, a header with the name of each sensor axis, and each row after that the collected data from the accelerometer plus the gyroscope, in a classic CSV style of file. We can also better visualize the data contained in the CSV files by using graphs. Take the biceps curl as an example. The z-axis of the gyroscope has a greater variation of degrees when compared to the x or y axis. Something unique to this exercise that will probably have a great impact in the feature extraction when developing a model. Talking about developing a model, all the data collected can be uploaded to the Edge Impulse website to develop a classification model. In this project, we have the ability to classify it in a binary way or in a multi-class way. What this means is, the binary way will output the exercise classification in either correct or incorrect classes, and the multi-class will output the classification in 4 classes, one for each exercise being done correctly, and one when any of the exercises are done incorrectly. In this project, we decided to use the multi-class model since it will provide a better feedback when making inferences. The DSP can be done by using either FFT or wavelets. It is important to note that in the binary model, the DSP done by wavelets had a better performance, but in the multi-class model, FFT and wavelets had almost the same performance. As this page shows, the performance obtained when training a model by using FFT and wavelets in the spectral analysis is mostly the same in the multi-class model. Something important to notice here is the great accuracy achieved in either case. And even though 80% accuracy is not ideal when performing a test using the testing dataset, it is good enough for now and means that there is room for improvement in our model. So, having the model complete and loaded on the board, we can begin making inferences. This diagram better represents how the inference result will be displayed. By receiving a command, the microcontroller starts analyzing data from the accelerometer and the gyroscope. After 8 seconds of exercise, it sends the result through Bluetooth to the smartphone. Displaying the information received by the smartphone can be done by using a simple app made in the MIT App Inventor that will show on the screen if the exercise was done correctly or not. On the video on the left, I execute the exercise in the correct way, displaying a thumbs up on the app when the inference is complete. On the right, I execute in an incorrect way by swaying my upper arm instead of having it fixed on the side of my body, displaying a thumbs down on the app when the inference is complete. We want to express our gratitude to CNPq for sponsoring our projects and ideas, and Seed Studio for providing us with the development boards used in this project, and also everyone who has helped us somehow along the way. We hope that our product will help people achieve better results in their workouts and motivate them to maintain a gym routine. If you have any questions, please ask them in the chat and I'll be happy to answer. Thank you.